friction is going to be known. We'll have h1, h2, which are the heights here, and this angle theta is also going to be a known variable, this theta here. And what we want to find is this distance r. And I'll try to keep color coordinated here so that you'll see that maybe everything in green will be a known, and then everything in blue will be something that we need to solve for, an unknown. All right, so the first thing to do in this problem is really the distance or the traveling from here to here. And we could use the principle of work and energy, but maybe you haven't gotten there yet, or you're only taking physics. And so we're going to use the equations of motion, or F equals ma. So the first thing I want to do is draw my free body diagram. And one more thing that we have to note here is that it starts from rest. So it's released from rest, and we're going to assume that this particle has enough mass and the angle is enough inclined so that it doesn't stop in the middle of the ramp. But when we solve this symbolically, we can even do what's called a parametric study. But anyway, I'm getting all crazy. All right, here we go. So here, I'm going to draw my free body diagram of this particle from the beginning where it's released from rest and between somewhere where it leaves a ramp. So somewhere in between. So here is the particle, and this angle is theta. And what we have in between here is that I like to draw the external force side and the inertial side. And I want to label my coordinate system. So here, positive x will be down the ramp, and positive y will be perpendicular to that going. So are the weight, W, a normal force from the ramp, and a force of friction. And then here, for my inertial terms, I would have M-A-Y and M-A-X. And one of the things I know about this is because this particle is being released from rest, and all the forces acting on this particle are constant, so the force of friction is not varying, the normal force won't be varying, the weight is not varying, it's mass times gravity. So I know that my acceleration of this particle will also be constant, and that's really important later when we do kinematics. So here, because my particle is only moving in one direction, the acceleration of y is 0, and now I can just write the equations of motion. So one of the challenges is always the geometry, and so just to make sure that we're all on the same page with respect to the geometry, I know that this line right here, which represents the rest of the ramp here, this portion has an angle theta right there. And so if I just draw a horizontal line right here, I know that this is also the angle theta. I know the angle between the y and this horizontal is 90 minus theta, and which makes this also theta right here. And so now I can write the equations of motion using the rectilinear coordinate system. And so here, so if I go ahead, I'll do sum of the forces in the x first, and this would be W sine theta minus FF equals MAX. And in the y direction, minus W cosine theta plus the normal force of the ramp equals MAY, which we know is 0, so this whole term equals 0. And we know that the force of friction here is the coefficient, the kinetic coefficient, times the normal force in the ramp. And in this case right here, let's see, based on what's given to me, I know W, I don't know if you can see that, W, I know theta, I know mu k, I know the mass, and my only unknowns in this case is the normal force on the ramp and the acceleration in the x direction. Alright, so I have two equations, two unknowns. That means I can use both of these equations, and what I really want is solve for the acceleration of x. If I rearrange, I solve here, and I substitute this normal force into that equation of motion in the x direction. Alright, and so again, my masses are known, but you know what, I can divide through my mass because every term has a mass in it. Hey, alright, and let's see, I know gravity, check, I know theta in this case, I know mu k, I know g, I know theta, and so now I can solve for ax. Ax is an unknown that I solve for, so ax is equal to, and let's see, everything that I know is g sine theta minus mu k g cosine theta. And this is the acceleration of the x, so I'm able to solve for it, and everything in green means I know it. Alright, so I'm good to go. I've solved for the acceleration of the x. And now that I know what the acceleration is, and if I look at it, as long as the angle theta is constant and the coefficient of kinetic friction is constant, then I know that my acceleration here is constant. And so I essentially have a 1D motion with a constant acceleration. And so I've got all kinds of choices to solve for the velocity right before it leaves the ramp. So the next thing I want to do, I'll call 3. And what I have here in this case, in this 1D kinematics, is I have an acceleration, which is my acceleration, ax is a constant. So it's just a number. And that means I can use all these 1D motion equations. As a quick refresher, if y'all write some out here, we had, like, if this was, if I wanted velocity as a function of time, I would change that constant to AC, so I don't have to write as much. So these are popular equations that come about from just integrating, and then if I solve for time here, and I substitute to get rid of time in this position equation, if I combine these two essentially to get rid of time, I would get that Vx squared. I would get this right here. And this xf minus x0 is delta s. This would be the change in position, delta s, at least according to what's given to me here. And so if I use this relationship here, what I have is, let's see, I will write this relationship out one more time. I'll have, in terms of delta s, and what I have right now is that, let's see, I have delta s, it's given to me in the problem statement, and I solve for ax in the previous step using my equations of motion, and obviously I know the number 2. Alright, and let's see, and I know my initial velocity because it starts from rest, so I'll call this v0, I'll put it in green again, it's in green, and I can square that number, obviously. Alright, and so what I have is an unknown vx that I need to solve for. I need to solve for this business right here, and that is just really a plug and chug, and so vx, if I just rearrange those, vx is equal to, this is the velocity as it leaves the ramp, is equal to the square root of 2ax delta s, 2ax times delta s, put a little dot there for the times, plus v0x squared. But in this case, right here, because it starts from rest, this initial velocity in the x direction is 0. And so basically what we're saying is that the velocity in the x direction as it leaves the ramp, after it travels a distance delta s, is AX, which is, again, we solved it previously, times delta S. All right. And if you really needed to, you could plug in this G, all this business right here, and that would just be, man, that's going to look a little nasty. But this will be square root of 2 times delta S times G sine, I factor out a G, make my life a little bit easier, 2 times delta S times G times sine theta minus mu k cosine theta. Yes, wow. Look at, because I'm doing things symbolically, I look all intelligent, but really this is just a number, all right, with the velocity, the initial velocity equal to 0. So Vx now is just a number. Ayo. All right, so now we got to do the projectile motion problem from here. Oh, snap. Guess what? So here, if I have H2 right here, obviously, can you see that H2 and delta S are related by theta? So essentially, even though I said H2 or delta S is given, H2 is given, they're all related. So if I wanted to put everything in terms of H2, I could also say that delta S is equal to, let's see, sine theta. I know that sine theta is equal to opposite H2 over the hypotenuse delta S. So I can also say delta S is H2 over sine theta, like this. And I can go back all the way over here and plug that in. All right. Oh, this is like punishment for doing things symbolically. All right. It's all good. So this is what, and everything again is still known here. Life is good. And now I have here in the projectile motion problem what I have is, so in the projectile motion problem what I have is this Vx, this crazy working equation right here, which is really just a number. Again, Vx, I have this particle leaving at a velocity of Vx here. And I'm just going to call that, if that's all right with you. Now, in the projectile motion problem, I will say that V0 is equal to this new initial velocity. In fact, here, maybe I'll make life easier. Yeah. I'll call it V0. It's all good. This new initial velocity for the projectile motion problem. In fact, I'm essentially, and this probably is a brand new problem, and I'm given from here that V0 is the Vx from the previous problem. It's this crazy looking number. This is my velocity. And I know this height here, this initial height, I think I called it H1. H1, right here. And I want to find R. So given this initial height, I'm even given the angle at which this velocity is happening here. So this velocity, boom, this particle is moving right here. This is V0. And I know the angle theta at which it's leaving right here, boom, theta. So I'm also given theta in this case. That's unknown. And even though the dotted line is like the path of the projectile is off the center of mass of this drawing, right here, we're going to assume that again, that the particle is so little that we will just make it one line. So in fact, if you feel better, I can draw the path right here like this, and I can erase all this other business. Oh no. All right. And so now I want to establish, let's see, for my projectile motion problem. Again, now I have all these things. I have the angle, I have H1, I want to find R, I want to find the horizontal distance that it traveled. And so here, to find R, let's see, I'm just doing a projectile motion problem. So the first thing I want to do is establish a coordinate system. And so here is I'm going to choose my origin of the coordinate system to be here, where my particle starts. Boom, right here. Here is X. Here is the Y direction. Right here, that's my new coordinate system for the projectile motion part, and my initial and final coordinates. So for my initial coordinates, I have, let's see, here for my initial coordinates, I have X0, Y0, and this is going to be 0, 0. And then my final coordinates, XF, YF, where my particle lands. So here's X0, Y0, and right here is XF, YF, right here, my final coordinates. And that is going to be, again, we're assuming the particle is infinitesimally small. This is, the particle is essentially right there. Don't judge me, judge yourself. Here, and here I start, again, this and this are the same point, all right, 0, 0, you have to believe me. This would be R, and this would be negative H1. This is my final coordinates, okay? R and negative H1, the horizontal distance in negative H1. And I know H1, but I don't know R. That's what I'm trying to solve for, all right? And so now I look at my 1D motion, and this is like curvilinear motion. I break up the motion into two. So here I look at my horizontal motion right here. And in the horizontal direction, let's see, I have acceleration is 0, and my horizontal velocity, Vx, would be V naught x. And here, that just means that horizontal component velocity is constant the whole time, which would be, if I want to really compute this, again, I know V0 would be V0 cosine of the angle theta right here. And the horizontal position equation, which is what I'm really interested in, is xf is equal to x0 plus V0 xt. And again, if I make the appropriate substitutions, xf here is r, this is equal to x0, which is 0, and I know it in this case, so this x0 plus V0 cosine of theta times t, which is unknown. And see, in this case here, x0 is 0, so I'll put that 0. So r is equal to v naught cosine theta times t. Now I look at my vertical motion, and this, we'll say, is positive upwards, and the acceleration in the y direction is negative g. All right. And again, if I were to write my velocity relationship, this would be vy, v0y minus gt, all derived by integrating, and here would be, and the position equation would be yf equals y0 plus v0y t minus 1/2 gt squared. And again, v0y is something that we know because it's equal to v0 sine theta, and based on the direction of v0, it would be negative v0 sine theta. We have a negative result. And so I could go ahead and substitute all this business here. I would have YF. Over here, let's see. I know YF. YF is negative H1 is equal to Y0, which we knew already, Y0, and we were 0, but here it's all good, I'll just write it for now. And then V0Y is negative V0 sine theta times T, which is unknown, minus, I know the minus, 1/2, I know that, I know G times T squared, yes, and what? I have one equation, one unknown here. This is getting ridiculous symbolically. I wish I could just throw in some numbers right now, but I'll leave that up to you right here. But I've got essentially a quadratic equation here, all right, and I can solve, I'm probably going to end up being able to solve directly for R right here. And so if I think about this, let's see, Y0 is 0, yay, like this, and I put things together here with this equation. This will be, let's see, I'll solve it for 0, is I'll bring the H1, so this will be H1 minus V0 sine theta times T. And my unknowns right now are T, which is circle here, and then the distance R. Alright, so if I go through some solving, I'll rearrange this first equation, the horizontal motion equation here, I'll call this like 1, I'll call this 2, so I'll rearrange 1, which would look like this, just to solve for time, so it'll be T, and then I substitute this time into 2, and this would look like, hey, look at those V0s are going to cancel out, that's convenient, hey, alright, hey, there it goes, and now if I just, now I got to solve for R, so here, let me simplify this equation a little bit, sine theta over cosine theta is tangent theta, alright, and now you can set up a solution for R using, which, man, this is like crazy, no wonder students want numbers, I would want numbers too, dang. I think this is it. This is pretty whack. So here, I think this is the solution for the distance. I hope not, but if it is, it's terrible. And I hope I made a mistake somewhere and that it simplifies even better. But this is for you, Jay. And here, check this out. Check this out, man. Let's see. This V naught business way back up here. This V0, you can substitute that back all the way into here for V0 if you wanted to, which, oh snap, so V naught squared is this business right here inside, and then you can, have things all in terms of just the variables that were given at the beginning of the problem. Hopefully that was fun and somewhat interesting and not too torturous. Let me know if I made any mistakes. If you like what I'm doing, I hope you will subscribe, like, and share the video. Let me know if you have any questions. Take it easy. Structure free. Hey, what's going on? Welcome back to Structure Free Office Hours. In this video, let's see, we're going to talk about torsion, alright, and we'll just do an example on torsion in our office hour session here. So the first thing, you'll be given a problem, it's like in 3D, right? And so, well, in this problem, I'm given some sort of rod that has a bunch of torsion loaded from, let's say, a bunch of gears connected to it, and it has a diameter, it's a solid shaft, it has a diameter of 40 millimeters, and I want to find the absolute maximum shear stress, tau max, along the shaft, and then it says I want to draw the shear stress distribution, and maybe we'll even draw a differential volume element. So I'll show you what that means, like drawing a differential volume element. But that's not essential right now. That's going to be more important when we do like, like stress transformation and things like that. Okay, let's see. So the first thing is to interpret usually a 3D drawing into a 2D torque diagram. Okay, so here's this schematic, defaulting schematic, and / FBD here. Here's default pen, touch. So here, I will stand as observer here, looking at this, so A will be on the left, and this is what the rod would look like. Okay, and I'm not going to draw the gears in, but I'm going to draw the concentrated torques. Okay, and let's see, the first one is if I use a right hand rule and I curl my fingers in the direction of the arrow, at point A, it's applying 15 Newton meters. At A. And then at point B, I have, this is B, CD, C, D, and E, and let's see, E is curling into, so this would be here, it would be E at E of 70 Newton meters,